I'm Marc Sturlese. I'm a software engineer focused on R&D, working at Trovit currently. And I'm responsible there for all the search and scalability infrastructure. And well, today I'm going to talk especially about how we migrate our architecture from MySQL to Solr, but not just going to talk about that. First of all, I'm going to explain what's Trovit, why we choose Solr and Hadoop for core engine, and then I'm going to explain all the data flow that our documents suffer since we collect them from the network or from feeds provided for our clients till they are indexed. Then I'm going to explain with detail the distributed indexing strategy we're using based on Hadoop. And then I will talk about how to move some interesting features that Solr has built in and that can be useful to put them outside of Solr, to use it with Hadoop, to be able to scale with a lot of data. I'm going to talk about text analysis and the duplication Solr feature. Finally, I'm going to speak a little bit about some important points to take into account about the indexing performance. And then there are going to be a few minutes for questions. So, what's Trovit? Well, Trovit is basically a search engine for classified ads. We're a tech company located in Barcelona, so here I'm local today. And well, it started like 5 years ago, just in one country and in one business category, but it was real estate. And well, today, after 5 years, it has changed a little bit. We are now in 33 countries and 4 different business categories. We're in real estate, autos, jobs, and in some countries, products. And well, the main purpose of the company is to serve good quality results to the end user as fast as we can, helping him to find a flat for renting, a second-hand car, or find a job. So here we can easily see what Trovit is. It's search results from a main page. We can see we are heavy users of Solr. We can see at the left that we are using Solr faceting, facet fields, query fields, date facets. We are using as well the more like this for recommending, highlight. But well, the talk today, it's not about the Solr out-of-the-box features. It's more about scaling. So let's keep going. Why we choose Solr and Hadoop? Well, in the beginning, we start with a custom-made Lucene search server. And it was working pretty well, actually. But the thing is that every time we need to build some new feature, it was taking a long time. Because, well, learning the APIs of Lucene was not easy. It was changing. Once you have done the feature, you have to be sure that it performs well. And then we discovered Solr. It had a great community, and it was pretty extensible. I mean, it's very easy to write plugins or wherever you need. So we just decided to make the move, and we are pretty happy with this. And then, as data store, we're using MySQL, and we used to index using the data import handler. We had a custom one because when we were doing incremental indexing, we were experiencing so many performance problems, many out of memories and horrible stuff. So we just built one that was working more or less properly. But the thing is that crawlers never stop picking documents from the internet. So the database was growing. And actually, in a while, it stopped working again. So scale up was really not the way. We're looking some MySQL sharded strategies, but they look actually pretty difficult to maintain, especially if you want to add a MySQL node to your MySQL cluster and you want to rebalance the data, I think you can die there. So we start looking at other options. We discovered Hadoop. It was scaling horizontally. In the beginning, we didn't know exactly what was that. But at the end, it was a good fit. So the data flow. Basically, our documents are crunched from a pipeline of MapReduce jobs. Since we collect them, well, actually, when the crawlers collect them from the network, till the documents are indexed, everything is done with MapReduce jobs. Okay. For each of these MapReduce jobs, we are always saving stats, because it's very important to know what happens every moment. I mean, we have seen that working with Hadoop, if you create really large pipelines, sometimes documents can be lost or changed and you don't know exactly why. And it's very important to keep track of what's happening in every job. And to get these statistics, we are using Hive. Hive is an Apache project as well. And it allows you to query your data from HDFS in a SQL style. You just write a SQL query, and internally, it creates a MapReduce job and returns you back the results. Well, so this would be an overview of our pipeline data. Ads are coming from, as I said before, the network or supported by our clients as feed types. And first of all, there's a ad processor job. This one does everything that it's monolithic and related to an ad. For example, discard fields that are not good, add some other special fields, everything that it's just depending from one document, from the single document. So once you have processed the document, there's this diff stage. Here, as you can see, the diff stage receives as input the output of the ad processor, but it actually receives as input the output of the next job from the last execution. Why do this? Well, as you can see, here I've put that this pipeline is executed in time t, and diff receives the input from time t and t-1 from expiration. That's because it's the way we have to realize if a document has changed from the last execution or is new. Or for example, if you're dealing with a feed and you receive an ad from the last execution and you don't receive it in the new execution, it means that you have to expire this ad because the client is not providing the feed with it anymore. So the diff mainly works for detect modifications and expirations. Then we have the expiration phase that basically it removes all the ads that are marked as deleted and even have some logic rules to expire documents that has expiration date and are not useful anymore. And then we have the duplication phase. I will explain this one later with a bit more detail. But we try to do the duplication in the same philosophy, the same style as Solr deduplication feature works. And finally, well, we have the indexing phase. That's the one that it's two stages, and I'm going to talk a little bit about this now. Once the pipeline is complete, imagine this box of pipeline as all this sequence of MapReduce jobs. We have to deploy the index. Okay, we always build the index from scratch this way. So what we do is first of all, we send them to an index repository. An index repository, it's just a simple machine with lots of teras of data. And then, using a multicast system, we deploy all this index to all the slaves at the same time. This multicast has been really helpful because in the beginning we used to sync them to the slave using rsync. But as we are building them from scratch, and we have many replicas, I mean, we have an index for each vertical and each country, and depending on which ones are, we can have shards of them. And when we were building all them from scratch, it was taking like ages to deploy to all the machines. So with multicast, you are deploying always to all the machines at the same time, and it's pretty much fast. So this pipeline is very nice. I mean, it's scaling well. You want it to be faster, you just throw there more machines to the cluster, and it works good. But what happens, I don't know, if the pipeline, for example, takes like 3 hours, this means that during these 3 hours, you're not going to get any new document in the index. So it's not really real time at all. And that's because we create the minimal data processor to provide to the system with something similar to near real time. What we do here is that for some special data, the one that we consider is the more important or the more new, we get it straight from the incoming data, do a minimal processor. It would be like something similar to the add processor, but simplified. And then we update directly the index repository. These updates normally are very short, not of so many documents. So here, we can rsync the changes to all the slaves. This is good, actually, because we are keeping doing rsync, for example, let's say every 20 minutes. And you know that you're not going to hit any strong merge, because your index has been built from scratch. And the new documents that you are adding are always creating small segments, and merges there are going to be small. So, wrapping it up, we have the indexes constantly built from scratch. It's actually very nice, because before, if you have to do a change that affects to all the documents in the index, we had to build it from scratch, doing selects in MySQL, and it was awful. And with this system, we have no problems. And as I explained now, you always are with the desired number of segments. So knowing that you have the segments, well, actually, if you know the number of segments, you can be sure that you're not going to hit problems during search time in the slaves. The minimal data processor allows us to keep updating index, simulating something like real time. And another advantage is the HDFS makes backups really convenient. As it has replication, every data there, it's replicated 3 times. So the chances of data corruption are very low. And then the other thing I explained is that this multicast system, it's very good to deploy to many replicas at the same time. The only limit there is your bandwidth. Let's talk now about the indexing strategy. In the beginning, to index with Hadoop, we start looking at this Jira, this patch, the Solr 1301. And what it does is that it extends the Hadoop API, extending the input format. And this patch allows you to create 1 index per reducer. Okay? This is good if you want to build a huge index, and you want to, each shard is going to have exactly the same shard, the same size. Because in Hadoop, a job doesn't finish until the last reducer have finished. So having the shards of equal size, it's convenient to end up as soon as possible. Well, this reduced site indexing looks good, but in our use case, we have many different indexes, some of them sharded, some other not. Some of them are pretty small, some of them are huge. So it was not working. We couldn't afford 1 reducer per index. So what I'm proposing, it's a different approach. It's a 2 stages indexing. And it means 2 MapReduce jobs. The first one, I've called it the partial indexing. And what it does, it just creates hundreds or even thousands of small indexes. I mean, for a monolithic index that it's big, you're going to create a lot of micro indexes. I'm going to call them micros, not to be saying indexes all the time. And for a small index, you're just going to create like a couple of micros, or even less, or even more, depending. And the second stage is the merger. Here what you do is just you collect all the micros that belong to the same index or the same shard, and you just merge all of them. So you end up with a monolithic index or with your shard. Well, this would be an overview of how this indexing strategy works. Up there, we would have our data, serialized data in HDFS. And the first stage would start creating these micros. Okay? As we see, the color shows us that they belong to the same index. Okay? So for a very huge index, like it could be, I don't know, real estate UK, we are building a lot of micros. And for a very small one, which could be, I don't know, cars Spain, for example, we're just building one micro. And in the second phase, we just merge all the micros. Okay. The advantage of this is that it's much faster to merge different index than to build a huge one. So, in MapReduce terms, the map would read or serialize data, and would group by micro. Okay, to decide how many micros you want to build, you just need to know how many documents will your index have. Okay, and the reduce receive these micros and merge them together. Sorry, no. The map emits for the micro, and the reducer receives all the ads belonging to the same micro and builds the index. Okay. So to build this index, we use embedded Solr server, and we build the index and optimize them. Then we upload it to HDFS, because to build these micros, the reducers ask for local disk space, build the index there, and then uploads it to HDFS. The Solr core configuration is stored as well in HDFS and must be downloaded to local disk as well. We do that because, well, trying to build indexes in HDFS would be pretty not performant, because Hadoop is not really good, not really fast at doing 6. So that's why we do this way. Well, if you're familiar with Hadoop, this is going to make a lot of sense. This is the schema how the job is built. The map, as input, receives as key the ID of a document, and the value would be the document itself. And the code here just has to decide this document to which micro must go and output it. So the output would be the micro index ID, and the value would be the document. So in the reduce size, what we do is, as input, we receive a micro index ID and all the documents that belong to this micro. So the code of the reducer is the one that specially is going to prepare the index and build it. The output in the reduce, it's not important at all, because in this job, we are responsible to ask to Hadoop for local disk, build the index, and upload it to HDFS by yourself, not using the context-wide function. So the output here, I just put a null key, and the value is a message that would be a random block message or whatever can be helpful for you. But it's not needed to build the index. Once we are done with all the micros, what we do is we list all the files that are in the folder where we have placed the micros and persist it to disk as a new file. So what we get is a list of all the micros, all the path to all the micros. And this is what the merge indexing is going to receive. Let's talk about this. Well, the merge indexing, it's done in plain Lucene. I mean, probably you can do it as well with Solr, but as we don't have to deal with analyzers in this phase, and I didn't want to create new cores and stuff, I just did it in plain Lucene. Okay. And the map, as I said, it reads the path of the micro-indexes and emits them for the main index to where they belong to. And the reduce side receives all the paths of the micro-indexes, download them to local disk, build the index, and upload back to HDFS. Okay. Since Lucene 3.1, the addIndexes function, that is the one that merged the indexes, just works with plain copy. It doesn't do merges. So if you have your partial indexes optimized, and you can afford here not to do merges, this addIndexes is going to be really fast. The thing is that if you end up with too many segments, you will have to do the regular merge. So the code of the reducer side of the second phase. And the map as input will receive a path from a micro-index, and the key would be the number of the line of the file. And the code here just have to get the index name where this micro belongs to. So it's going to meet the index name and the micro-index path. In the reducer, we're going to receive an index name, like it would be real estate UK, and a list of paths to all the micros that belong to UK real estate. So the code here just have to download the indexes, merge them, and upload. And as I said before, in the first phase, in the partial phase, the output here is not important at all, because we are the responsibles to upload the index to HDFS. Well, pros and cons of this indexing strategy. Well, it's highly scalable. It's the main advantage. I mean, it allows us to build all the indexes from scratch in a very fast way. And what it has that it didn't have the Solr patch is that it allows you to build indexes from many different sizes. Okay? And, of course, it's very easy to manage. I mean, with Hadoop, everything that you build, at the beginning, it's like a little bit difficult, but once you are done, it's perfect to scale and easy to manage. You don't have to control anything of masters and slave. Everything is dealt with Hadoop. And, well, the main con is the time you spend uploading the partial indexes in the partial side or the whole index in the merge side, and the time you spend downloading the micros in the merge side. It takes time, but, well, the good part is that, as I said before, we have this minimal data processor that when the pipeline is being created, the indexes in production are still getting updated. Well, let's talk now about moving some features outside of Solr. Well, we decided to do that actually because we had to deal with a lot of data, and it's when it was especially useful to have. Okay, I'm going to talk about text processing with Hadoop and Solr, and Solr distributed deduplication. Well, text processing with Solr and Hadoop. Solr has a lot of powerful analyzers already built in, and sometimes you maybe need to use them or would like to use them outside of the box. I mean, you would be interested in tokenize some text using the Solr analyzers, but you then don't want to build the index. You want to do whatever you want with the data. Right? Actually, Mahout uses plain Lucene to tokenize some data and to build vectors and stuff. And what I did was exactly the same, but using the Solr analyzers, because Solr has much more analyzers than Lucene built in, with many options, many features, and they are really easy to use. So what I do is, in the setup method of the map, I instantiate an analyzer. And then when the map keeps receiving the serialized data, I can use the Solr analyzer to process all the data. And as you configure an analyzer with Solr using the schema.xml, You can use the Hadoop file configurations to configure there your scheme as well. Well, here I just put the snippet of code. Not going to go in detail, but it's just in case someone is interested how the code looks like. Here we just create a word delimiter filter. It's the one already built in Solr. We just add there some other filters as lowercase filter, isolating to remove accents. We configure the word delimiter getting parameters from the Hadoop configuration. And finally, we create a tokenizer chain that it's going to be our analyzer. This is to get the instance. And then to use it, it's even easier. You just need to create a token stream and iterate over all the tokens, and you're going to get them analyzed. Distributed deduplication. Actually, when we start using these two stages indexing strategy, we couldn't use the Solr deduplication building feature anymore, because as we are building like small indexes, we just would be able to calculate the duplicates inside these micros, but not in the merger side. So what we do is to port this feature outside in another MapReduce job that, as I said before, we run it before the indexing phases. Here, the map just would receive the serialized documents and would build a key that it's the same as the signature, the text profile signature built for Solr to detect duplicates. Then the reduce receive all the ads grouped by this signature, what means that all the ads that are grouped in the same group are going to be duplicates. And as you configure the duplication in the Solr config file, you can use here as well Hadoop configurations to receive all the parameters you need. Like, for example, which fields you want to take into account to decide if two documents are duplicates or not. The MapReduce job would look like this. Would receive, as I said before, as input. Key value would be the ID of a document and the document itself. The code here is responsible for building the signature, just this. Just build the signature and emit it as the key. And the value would be the document again. And then in the reduce, the key would be the signature. So for each signature, we're going to receive a list of documents. And this is actually a bit more powerful than Solr deduplication. Because with Solr deduplication, you just get one document. I think you cannot choose one. Just you're going to index the newest one that comes to the index. And sometimes this one may not be the best one. For example, if you have two documents and you have to choose to decide if they are duplicates or not, the title, the content, and the city, maybe they are duplicates, but then one of them has many other fields, like address, region, wherever, so it's more richer. And you're interested in make this one appear in the index. So here it's very easy to do that, because you receive in a group all the documents, and it's very easy to decide which one is the one that you're going to emit. Another option, for example, is to, instead of writing as the output value a single ad, you can, with your serialization system, like Abro, Thrift, or protocol buffers, wherever you want to use, you can build a list of ads, an object that is a list of ads. So you can emit all of the duplicates in the same object. Then in the index, using multi-valued fields, sorry, you'd be able to index all the duplicates in the same document. I mean, that's another option. There's plenty of options here. You decide. Let's talk now a little bit about performance, indexing performance. I'm going to talk about the merge factor. Merge factor is a parameter I've found very, very useful to understand how it works, because it can speed things up in search or in indexing time. It depends. This merge factor parameter is used in the log byte merge policy and older ones. Okay. And at indexing time, it tells Lucene how many segments can be created before a merge happens. What does it mean? Well, for example, if you set a low value to the merge factor, the minimum is 2. What's going to do is every time Lucene creates 2 segments, it's going to merge them together. What happens here? It happens that indexing time, it's going to be higher, okay? Because there are happening lots of merges. But then, as you have less merges, when you deploy your index, the search time probably are going to be faster. Because the less segments you have normally, the faster the queries are. And what happens if you use a high value here? Well, so just the opposite. As less merges are happening, the index is going to be built much faster, but then queries may be slower. So you have to balance here what fits best for your use case and decide what to do. Actually, new versions of Solr default to the tiered merge policy. They are not using by default log byte merge policy anymore. And this one works slightly different. Log byte merge policy used to just merge segments that are contiguous. And here with tiered merge policy, and it decides which are the segments that is best to merge them. Okay? This merge policy doesn't use merge factor anymore. It's configured with some other parameters. But well, I think it's interesting to know how merge factor works to be able to configure this one very similarly. Actually, it doesn't differ that much. And well, that's it. Okay, so hope you enjoy it.